So the next type of our nonlinear programming models are the advertising response and selection models. The response models use the historical data in the response function to predict the future customer responses or exposures based on the exposure to the number of ads or overall level of advertising expenditure. The selection models determine the optimal mix of ads during different types of viewing opportunities in order to minimize the total advertising cost, stay within budget, and meet the required viewership levels. Okay, so that's sort of described here towards the bottom of them. We're not going to have any example of these, right? Because it's really more complicated. But each one of these different shows during different times in different locations will have different response functions. We're going to concentrate on response functions themselves towards the top, right? We're going to start with that response model function, as I just said, showing the how the additional ads have a decreasing marginal value and demonstrate a simple process of estimating response function parameters. Then we will look at the ad spending model on a simple example based on given customer response functions in class rather than in these videos here. Okay, so the simplest response function is a concave curve right here, shown in the top right corner of the slide, and has a format of f of n right here equals a times 1 minus exp of negative b times n, right? Where n is the number of ads in a given time period. Okay, a is the estimated maximum exposure on which there's no measurable effect of throwing more advertising dollars. Okay, the b right here is the speed at which the saturation occurs. Okay, so it's sort of similar to that power curve where the b measured how fast the demand decreases as the price increases. Okay, and then that's it. All right, so the slightly more complicated um, advertising response function that we're not going to use, but it's used quite a bit, is the so-called S-shaped curve right here. It looks like an S in the bottom right corner of the slide, where the idea is that it takes a little while for the model to ramp up, and then sort of becomes this concave curve that we were just describing, and then the diminishing returns kick in once you spend beyond certain level. Okay, next we're going to use the empirical data on the number of ads and actual exposures to estimate the predicted response function using the method of minimizing the sum of squared errors between the actual and predicted exposure. The solver will then help find this minimum by changing the maximum and speed of a response, maximum response and the speed of response parameters A and B that we just described on the previous slide, right? So we're going to do that all in the elect6 underscore advertising file. I'm going to zoom into the top left corner where the actual response function based on number of ads from the past, so historical data is shown here on the right side, and shows that for a given number of ads, the exposures first grow relatively fast and then sort of start diminishing off, right? And these are presumably in thousands of millions. I don't actually remember. So what we're going to do, we're going to use the two orange cells, right, for our maximum exposure parameter A and speed of saturation parameter B, and we're going to make up something to begin with, right? Um, and maximum exposure appears to be somewhere here in the 100 range, so let's just type in 100. Where the speed of saturation is more difficult to ascertain just by looking at this chart over here, right? So let's put 1 just to have something for the parameter. Okay, and then what we're going to do is we're going to go into the predicted column C, and we're going to start with that single ad in cell A7. And I'm going to use that um, advertising response function f of n in this format, with A being 100 times exp of negative B saturation times number of ads. Okay, and I'm going to close that, and I do need 1 minus in front of it and then the end of it. Okay, the cells that need to be fixed are obviously the D4 and D5, D4 and D5. Okay, and that should give me a number, right? Which at the 63,000 million, whatever this number is right here, is obviously too high. So I'm going to drop that by an order of magnitude from 1 to 10%, which is still high, but closer to the actual exposure of 4,700 or 4.7 million um, viewers, right? So we're going to stick with that zero point 0.1 for a second. We're going to copy this down, and we'll notice that, of course, because of my maximum exposure of 100, this quickly ramped up and then leveled off literally at 100. What I'm going to do now is we're going to change the maximum exposure parameter to something like 150, which is then going to be a little closer to where that curve actually ends up here, but much further in this middle part of it, which means that the speed of saturation is too fast. It's ramping up too fast and leveling off too quickly. So I'm going to drop this by another order of magnitude, 0.01 from zero point 0.1, okay, and get something that's considerably closer, but still not, very closely aligned with the actual, which is the blue, right? So in order to get these parameters, right, we're not going to continue like this manually, but in order to get these parameters to be, the best in terms of the fit with the actual data, the blue points, right? We are going to use the method of figuring out the square errors, adding them up, and then minimizing them by changing these two parameters, the maximum exposure and speed of saturation. So that's very simple here. In the square error, we do equal actual minus predicted squared, or the other way around, doesn't really, I guess, matter. Okay, and then what we're going to do is we're going to pull those down, and then we're going to add them up. Okay, and then what we're simply going to do is we're going to minimize with solver. We're going to minimize that sum of squared errors by changing these two parameters a and b. Okay, and we'll assume that the unconstrained variables are non-negative. This is again a very smooth problem, so the standard GRG works, and the solver will quickly find the solution of 155 and 0.02 ish or so. So relatively close to what we had, but obviously much better aligned with the actual data, right? And then what we're going to do with these two parameters, now we're going to use these parameters to create a response model chart down here, okay, for any level of spending between 0 and 400, 400,000, whatever the actual unit is, in increments of 10, right? Starting with a times 1 minus exp of negative b times n, which n is the number of ads, okay, fixing again the a and the b, okay, obviously starting with a 0 and then getting the concave shape that we've seen on the slide here on the right hand side. Okay, so this does it for the advertising response model, and this is a good place